Alright. Hello everyone, and welcome to today's chem lesson. Today we are going to talk about covalent bonding and how we treat covalent compounds differently than ionic compounds. In a quick summary, covalent bonds occur between two nonmetals. This happens when the electronegativity difference is less than 2, and atoms share the electrons between them. They do not transfer those electrons and become ions as they do in ionic bonding. A lot of common chemicals are covalently bonded, right? Things like water, carbon dioxide, oxygen, methane, ammonia, all these things are covalently bonded. Sugar. And they have a whole different outlook and a whole different way of being treated than ionic compounds. Before we get into detail on what we're going to look at for covalent compounds, we are going to take a look at the properties of covalent compounds. Like we had with ionic compounds, anytime a new substance is created, it has a new set, an individual set of properties. Covalent properties pretty universally have these things in common. They are soft with low melting points and boiling points, and they are bad conductors of heat and electricity. You'll notice that these are pretty much the exact opposite of some of the properties we had for ionic compounds, where ionic compounds are hard with high melting and boiling points, and they are good conductors if aqueous or liquid. You'll also probably notice that these properties line up pretty nicely with what we know about nonmetals in general. Right? Nonmetals in general are soft with low melting points and boiling points. They're bad conductors of heat and electricity. And so when you bond two of them together, we keep some of those generalized properties, but they do get a brand new set of numbers, right? For example, if we look at hydrogen, oxygen, and water, the melting point and boiling point of these three things is not equal, even though one contains the others. Right? The fact that these are all non-metals means that they might share these properties, but the actual numbers, if we get into the numerology of it, is very different. Now, the main thing we're going to look at with covalent compounds is going to be drawing covalent compounds. We want to be able to look at a formula for a covalent compound and be able to draw that substance. Now, this means we're going back to Lewis dot structures, Lewis dot diagrams, and we are going to be using our template as we did in the past. Right? Element symbol goes in the middle, and we put dots around the symbol in a certain order to show where the valence electrons are. The goal when drawing a compound is to write the individual atoms and their Lewis dot structures. And then you want to try to find a way to connect our pieces together to make every electron look like a noble gas, to make every atom stable. Right? Nitrogen wants 8 valence electrons because it has 5 already. It wants to gain 3 more to get to 8. Hydrogen is an exception to the rule. Right? Hydrogen with only 1 shell only wants 2 valence electrons. And so what we're going to see is we're going to be pairing electrons together to try to make an overlap so that the N and the H can share electrons so they both end up happy. We're going to take a look at that in a little bit more detail. I'm just going to get rid of these words on the page here. All right, let's keep our template. All right, if I draw out nitrogen with his 5 valence electrons, and each hydrogen with their 1 valence electron. My goal here is to put these things together in a way where every lonely electron gets a buddy. Right, and now when we're talking about lonely electrons, we're talking about electrons that are alone on the side of an atom. Alright, so each of those is a lonely electron, and our goal here is to connect these 4 things together in one fluid molecule that pairs up every lonely electron. So what does that look like? I'm going to start with my N here. All right, we're going to take one of those H's and click it into place right there. Right, pairing up lonely electrons to create a bond. And so that means we've paired those. We're not quite done yet. We still have 2 H's and 2 more lonely electrons on the N. And so what I'm going to do is I'm going to take one of these H's and I'm going to turn it 90 degrees, knock it over, and put it so it clicks here, creating another bond. The problem with this is that a sideways H looks like an I. And we know that iodine is an element on the periodic table. And so we don't want our sideways H to look like a short I. Right? And so what we're going to be able to do, what we now have the ability to do, what we now have the permission to do, is to rotate our Lewis dot template. Right, we are allowed to rotate this template around the symbol, which means I can have 1, 2, 3, 4, 5, 6, 7, 8. Right, it's still the same order, but now instead of starting from the top, we can start from the left. Or we can do the same thing starting from the right side. Right, but notice, no matter where I'm starting from, the order still stays the same. Right, no matter which side I start from, I'm still doing this pattern. It's just now rotated around so that we could click more easily into place our lonely electrons. Right. By clicking in those last 2 H's, I have now paired up all the lonely electrons that I started with. I now have this picture here. And when I want to get to a final drawing, a final picture, I am going to replace every bond with a dash like this connecting the atoms. Right, and we'll, as we get more in depth with these, you'll notice it's just easier. You get a little bit more freedom if you're drawing with the dashes instead of trying to hook up all the dots at these perfect 90-degree angles. Right, it's more common to see this drawing than it is to see the dots like this. These bonds are still here, right? They still represent the same thing they did in our top picture. It's still 2 electrons, one from each atom, connected together. And so if we want to double check our work here, let's see how many electrons are touching this hydrogen. This hydrogen has 1 bond touching it, which is 2 electrons, which is what hydrogen wants. Remember, hydrogen is something that only wants 2 electrons. That's true of the bottom hydrogen and the right side hydrogen as well, right? Each one is only having 1 bond touching it, meaning that each one has 2 electrons. When we get to the nitrogen, now we have 3 bonds touching it, so 6 electrons, plus the 2 that were unbonded, making a total of 8 touching the nitrogen. All right, 2 from this bond, 4, 6, 7, 8. Every element here is stable with either 8 or 2 valence electrons. Every lonely electron is paired. Every lonely electron got a buddy. And so we have a final answer. If I move on and look at something like HCl, you can see pretty quickly that we have 2 unpaired electrons, right? 2 lonely electrons, and so we are going to buddy them up. We're going to end up with a picture that looks like this. Where I have again created a bond by clicking the hydrogen into place, pairing up our lonely electrons. And as I finalize my picture here, I'm again going to switch my 2 dots, right, my bond into a dash, and then making sure that I take everything else from the picture. Here again, if I go to double check my work, hydrogen has only 1 bond touching it, which is 2 electrons, which is what hydrogen wants. Chlorine has 1, 2, 3, 4, 5, 6, and a bond. So 6 plus 2, 8 valence electrons. If we come over here and take a peek at water, I'm going to use red for oxygen because I want to do that again later. Oxygen has 6 valence electrons, which are going to come through looking like this. Here again, if we go to point out our lonely electrons, we are going to have to try to buddy all of these electrons so that everyone is happy. And we can do that by clicking our hydrogens into place, one on the side and one on the bottom, creating 2 bonds. And leading us to a final picture that looks like this. Again, our oxygen now has 4 electrons plus 2 bonds. So 2, 3, 4, 6 from the first bond, 8 from the last bond. Right? Oxygen is happy. Our hydrogens each have 1 bond touching them. 2 for each hydrogen, which is what they want. Right? Giving us a final picture. Now, if we come to our last example here, we see CH4. And when we come along to draw CH4, we have 4 hydrogens, each with 1 valence electron. Then we have a carbon. Carbon with 1, 2, 3, 4. If we try to make our connections here, we are going to have a very difficult time doing it. And that's because carbon is an exception to our template here. Carbon is special. Carbon gets 1 dot on each side. And so instead of what we might want to draw, instead we draw this Lewis dot diagram for carbon. Carbon is the only exception, it's the only thing that this happens with. And now, when we connect, you can see we're going to get 1 lonely electron on each H, plus 1 lonely electron on each side of carbon. And when it comes time to draw our picture, we are going to be able to nice and evenly distribute our H's, clicking 1 into each spot, making 4 bonds. And leading us to a final picture that looks like this. Here, each of the hydrogens has 1 bond touching it, which is what they want. The carbon has 4 bonds touching it, each one of those bonds representing 2 electrons, for a total of 8 electrons around the carbon, making the carbon stable as well. You might have noticed that along the way here, each of our first 4 examples was hydrogen heavy, right? Each one of these had hydrogen as a main component. And so what happens if it gets a little bit more complicated? What happens when we don't have as much hydrogen? Let's take a look. Here are 4 more examples. Notice a lot less hydrogen is seen here. We're still going to keep some important things. Right? We are going to keep our template, so we can refer back to that. We are going to keep the reminder that carbon is special and gets 1 on each side. We are going to keep the reminder that we are allowed to rotate our template around so that it's easier to click our atoms together. And we are going to keep our little mantra of every lonely electron gets a buddy. And so with that, we're going to tackle O2, the oxygen that you breathe in every day. Oxygen has 6 valence electrons. And so we're going to draw it twice. We're going to mark off our lonely electrons. We're going to have to connect these lonely electrons together. And this is the first example of us needing to connect lonely electrons on the same atom, right? We're going to connect this red to this blue. And we're also going to connect this red to this blue. We're going to form what is called a double bond. So how is that going to look? We're going to have our oxygen over here with 6 valence electrons. We're going to take this red oxygen and rotate it 180 degrees. So we're going to go 1, 2, 3, 4, 5, 6. And we are going to connect, we're going to click this oxygen diagonally into the blue oxygen and end up with a dot here, a dot here, O, and our other valence electrons. And this is a little bit of a weird looking diagram, right? As we look at the bond that we make here and here, we still have 8 electrons belonging to each oxygen, even though it's a little bit more difficult to see. This red oxygen has the 4 that it's touching, this bond, and this bond, right? So 2, 4, 5, 6, 7, 8. The blue oxygen has its 4 blue valence electrons, plus both of these 2 bonds, right? So 4, 5, 6, 7, 8. But when it comes time to tidy up our diagram, we are going to actually shift this thing a little bit so it straightens out. And gives us a picture that kind of looks like this. Right? If we look for our line of symmetry here, I took this and I just kind of flattened it, brought it down so that it was in a straight line. Right, you'll see that the electron placement, right, there's 2 on top, 2 on bottom, 2 on top, 2 on bottom, 2 on top, 2 on bottom, 2 on top, 2 on bottom. And our bonds are still here as well. Right, this is a thing that happens pretty often, the fact of a double bond, one atom connecting to another more than one time. If there is a double bond and a single bond, which is what we were looking at before, then the odds are that there is also a triple bond. So let's take a look at that. If I have 2 ends and connect them together. Right here, in order to make this connection work and connect all of my lonely electrons together, right, if I want to find each of these lonely electrons a buddy, I'm going to rotate each of these 90 degrees so they kind of fall onto their sides. And we are going to end up with nitrogen and nitrogen. Nope. 1, 2, 3, 4, 5. And here, the connections that get made are right there. Top connects to top, middle connects to middle, bottom connects to bottom. And this creates a triple bond, which when we clean that up is going to look pretty similar to a double bond, except with one more line in it. If I go to double check my work here and look at my connections, this nitrogen has 2, 4, 6 coming from the bonds, 7, 8. This nitrogen has 2, 4, 6 coming from the bond, 7, 8. Right, both nitrogens are happy here with a triple bond shared between them. And if there's a single bond, a double bond, and a triple bond, maybe there's also a quadruple bond. But there's not. Right, triple bond is the highest that we can get to, sharing 6 electrons between 2 atoms. A quadruple bond can't happen, it's impossible. And so those are the only types we can play with. Double bonds are more common than you think, as we're going to see in our next 2 examples. If we look at carbon, which is special, with its 1 on each side, and our oxygens, which have 6 electrons each. I'm going to take a red and a blue again, just for consistency's sake. Are there supposed to be 2 on top of the first N? Right, there are 2. We turn the whole thing 90 degrees, so those are our 2. And then when we clean it up, those 2 stay here. Right, so there are 2 with the N. Right, but we are allowed to rotate our Lewis dot diagram. And so we're going to end up with these 2 electrons going here and then here. When we look at CO2 and everything is drawn out, we have a lot of lonely electrons that need pairing. Right, 4 on the carbon, 2 on each oxygen. And now you are more than welcome to try to connect these on your own, but the only way that you are going to find that works is by connecting each oxygen to the carbon twice. Right. If I show you pretty much the same thing we did here with O2, except now there's going to be a carbon in the middle. Right, and we are going to end up with connections occurring here, 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 here. And when this gets cleaned up a little bit, we are going to see again what we did with the O2, where we took it from its 45-degree angle and kind of flattened it out. We're going to have that happen here too, with carbon connecting to each oxygen twice. Right, and again, keeping this line of symmetry, which should be a straight line, but I can't draw those. Right, just taking this and bringing it down to a 180-degree angle, right, flattening it out. Checking our work shows us this oxygen has 2, 4, 6, 8 electrons. This oxygen also has 8 electrons, 2, 4, 5, 6, 7, 8. The carbon also has 8 electrons, 2, 4, 6, 8. And that makes every atom of this bunch stable and completes our compound. Our last example over here is going to, again, showcase carbon with its one on each side orientation. Hydrogen twice, 1 valence electron each time. And an oxygen, which we are going to get red for the sake of having it be a different color. We again have a bunch of lonely electrons that need buddies. And again, you can try as many different ways as you want, but you will find that there's only one way to connect these together. And that is going to look like this. I'm going to have to take my carbon in the middle. My oxygen needs to double bond. And then I'm going to put a hydrogen here and here, creating 4 bonds. All right, 1 here, 2, 3, 4. When I clean up this picture, I am going to end with something that looks like a Y. All right, with the oxygen double bonded to the carbon, keeping its unpaired electrons there, unbonded electrons. And then we want to try to keep the shape as much as possible. So if we're doing a straight line down this way, we're going to end up with a Y shape, trying to maintain these angles to the best of our ability. All right, we've got connection here, and then up through the oxygen. And we want to try to maintain that to the best of our ability. So our final picture for CH2O is actually going to look like this. And if we come back in to double check our work, we will see that the oxygen has 8 valence electrons. 2, 4, 5, 6, 7, 8. The carbon has 8 valence electrons. 2, 4, 6, 8. The hydrogens each have 2 valence electrons. Right, for each from 1 bond. And that makes each atom stable. With that, I am going to transition us over to our Google Meet for questions, comments, concerns, and attendance. And I will see you there.